Today we'll be doing the LabView tutorial on Bernoulli's lab, so go ahead and open LabView. Start at a blank VI, and I'm going to make the block diagram big. And we're going to go ahead and first insert the DAC, so make sure you have the DAC hooked to your computer already when you do this section. We're going to acquire a voltage, and we're going to acquire two channels, AI0 and AI1. They're both going to have plus or minus 10, and we're both going to use n number of samples. So for this lab, you're going to want to collect about 30 seconds of data. So you're going to go ahead and have to create a control for the timeout, the number of samples, and the rate. Now, you're going to want to make sure that you collect about 30 seconds of data for each run, like I said before, but you're going to have to select your rate and your number of samples. Go ahead and organize it a little bit. So now what's coming out of the DAC is voltage from the pressure transducers. So we're going to go ahead and just create a plot of that just to see what it looks like. And then we're going to take the average of it. So to take the average, we need to first split the signals. We're going to split two signals from it. And we're going to want the average and standard deviation. So I'm going to go ahead and find that underneath probability and statistics, and I'm going to use the standard deviation block. And then I'm just going to connect the first one to this. And I'm going to create an indicator for the mean and create the standard deviation for the mean, or the standard deviation. And I'm going to create an indicator for that as well. And this first pressure transducer is a dynamic pressure one, so I'm going to say dynamic press transducer voltage mean. And then down here, I'm going to do dynamic press transducer voltage standard deviation. I'm going to go ahead and organize this a little bit better too. Try and save as much room as I can so that later on I know what's going on. So now I have taken the mean of my first pressure transducer, which is my dynamic pressure transducer, and now I'm going to copy this and paste it below to save room. I'm going to change it from dynamic to static pressure transducer, because the second pressure transducer is a static pressure transducer. And go ahead and delete the mean number 2 off of these. And then I'm going to go ahead and connect that to the second one. And make sure I make it nice and organized so I can see what's going on. Alright, so now I've taken the mean, and I have the mean for both pressure transducers. So what we're going to do now is we need to calculate the pressure transducer based on your calibration curve. So now what we need to do is we need to insert a formula block, and the formula block is to convert the voltage to a pressure. So we're going to insert two formula blocks. Arithmetic and comparison formula block, and the first one's going to be whatever your formula block is, so I'm going to change the x1 label to voltage. So it's going to be, say, 500 times your voltage plus 250 for the first one, and your voltage that you put into this is the mean voltage. And make sure that you keep it so you can read where your wires are going. And then I'm going to copy this formula and paste it for my second pressure transducer. And this one is also going to be voltage, and you're going to use the mean pressure block again. And it'll be a different formula, say like 500 times a different intercept, like 240 instead of 250. And I'm going to try and save as much room as possible so I can show everything on the same VI block. So basically what you're going to do is you're going to run your VI block. You're going to run this VI. You're going to collect the mean voltage for both dynamic pressure and static pressure as you're calibrating them. And then once you calibrated it, you find your calibration curve, and then you take that calibration curve where you plot Y is pressure and X is voltage. You apply that equation, that trend line, that linear trend line for that voltage curve in this formula block for each pressure transducer. So you'll have one pressure transducer calibration for the first one for the second one. That way what comes out of here is actually the pressure. So I'm going to create an indicator, and this is relative static pressure in pascals. And then I'm going to create another indicator up here. And this one is dynamic pressure in pascals. Make sure you get your wires so you can see where everything's going. So now we've converted both of them to the relative pressure. And the relative pressure meaning the difference between the high and the low port. Now the next thing we're going to want to do is we're going to want to convert the dynamic pressure to velocity and convert the relative static pressure to absolute static pressure. And then once we calibrate the velocity and absolute static pressure, we can then calculate Bernoulli's constant. So before we do that, let's go ahead and organize our front panel. So I'm going to go ahead and move things around a little bit. So I have my data graph. Here's all my controls for the DAC. I'm going to go ahead and move those in one line. Then I have my dynamic pressure transducer voltage. Go ahead and organize that. Put it in the same row. So then I can put in that same row the dynamic pressure. So I can look across here and see the mean, the standard deviation, and then the dynamic pressure. And do the same thing with the static pressure below that. And now I can see the same thing. I can see the mean, standard deviation, and the relative static pressure. And I'll go ahead and move these down a little bit, and now I can center it. And then I can also see this probably on the right side here. If I do this, you can see pretty much everything. So now going back to the block diagram, I'm going to insert another formula block, and that's for the top one to calculate velocity, and the x1 is going to be pressure, or should I say dynamic pressure, and the second one is rho, density, and the equation is from Bernoulli's from the handout. It's the square root of 2 times the dynamic pressure divided by rho infinity, which means the density of the free stream. So I'll create an indicator, and this is velocity in meters per second. And then I need to create a control for rho, and rho is inserted in kilograms per meter cubed. So what I can do is organize this a little bit better, and I'm going to import dynamic pressure, which is calculated from the previous formula block. So now I have velocity. So now I go to my front panel and organize these. So velocity is an indicator, which corresponds to dynamic pressure, and rho infinity corresponds to a control, so I'm going to put it right below the rate. And then the next thing I need to do is calculate the absolute static pressure here, and the way I'm going to do that is I'm going to insert a numeric addition, because you have the tube for the static pressure on the high port, so you need to add in ambient. I'm going to create a control for the ambient. So I'm going to say absolute ambient, or should I say ambient pressure, and this is in pascals. And then I'm going to create another indicator, and this is going to be absolute static pressure. And that's going to be in pascals. And clean this up a little bit too. And then when I go to my front panel, reorganize this as well. Ambient pressure is also control. I'm going to put that right below the other controls. And then ambient static, absolute static pressure, I'm going to put right below velocity. So now I have from left to right my voltages, my standard deviation, my pressure, dynamic pressure, and my velocities. So the final thing we want to do for this lab is we want to calculate Bernoulli's constant. And we want to do it two different methods. You want to do it with considering gravitation and without. So we're going to go ahead and insert another formula block. Well, the first equation we're going to do is equation 16. The first label is our absolute static pressure. Our next label is velocity. And our final label is rho infinity. So it's the absolute static pressure plus 1/2 times rho times velocity squared. Then we got to add in rho times gravity, 9.81, times your position z, times your position or height. So I'm going to say height. And then hit OK. So that's the first Bernoulli's constant using equation 16. So I'm going to create indicator, and this is Bernoulli's constant. For equations 16 and 17, because the equations are equivalent. You're just replacing the static and dynamic pressure with the stagnation pressure and then adding in that assumption. Now we need to hook up everything. To do this, we're going to first take our absolute static pressure, then we're going to do our velocity, then we're going to do our rho infinity, and then we need to create a control for the height. So this is the height from the bottom of the channel, and this is in meters. And go ahead and move this around so that we don't cross the wires and you can read it better. So now the next one is we're going to insert another formula block. This time it's going to be changing the formula. We're just going to delete the second part, and you're not going to need this height. So you can just turn it back to x4 and hit OK. And then we're going to need the absolute static pressure. And then I'm going to copy this indicator and paste it. And then I'm going to rename it. And this is based on equation 18, which is just the stagnation pressure. So you're just adding your static and dynamic pressure together. Go ahead and move the wires again so they don't cross. And then tidy it up a little bit. All right. So now I'm going to insert my velocity first. And now I'm going to insert my rho infinity. And now I have both my equations that will give me Bernoulli's constant. So if I go to my front panel and go ahead and move these down so you can see them. And then move my height control to below the row. And then if I shift all this stuff on the bottom over, and then I now have a nice organized front panel. So again, when you run this, make sure that you save this data, and I'm going to go over that really quickly. But make sure that you're running about 30 seconds of data and you make your timeout greater than 30 seconds, like 40 seconds. And when you calibrate the pressure transducer, you're interested in these two right here, the dynamic and static voltage mean. And then you're going to record the height of the water column along with the mean voltage in Excel. Plot the pressure on the y-axis, the voltage on the x-axis, and then you're going to create a linear trend line, because it should be a linear response, and that linear trend line will give you an equation which you insert in here to convert voltage to pressure. So now I'm going to take all this and I am going to save it and label everything. So I need to probably reorganize everything. So I'm going to go ahead and see if I can get all this organized and be able to see it still. So now I'm going to start saving all this data. And this is where it's going to get a little bit messy. There's no way to avoid this. But as long as you have this hooked up correctly, then what we can do is the following. We are going to merge everything in a systematic way. And then we're going to name everything using our naming blocks. So I'm going to go ahead and just move over this wire. It's going to go a little bit behind the words and everything, but this is to save some room. So first, what you're going to need to save is the actual signal itself.
The next thing I want to save is the pressure transducer mean. Then I want to save the pressure transducer standard deviation.
The dynamic pressure, then the velocity. Then the next thing I'm going to save is the voltage for the static pressure transducer. I'm going to save the mean, and then the standard deviation. Then I'm going to save the relative static pressure. Then I'm going to save the ambient. Then I'm going to save the static pressure, the absolute static pressure. Then I'm going to save the row infinity. Then height. And now I'm going to save the first Bernoulli's constant and the second Bernoulli's constant. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 signals that I have to name. Right? So I'm going to insert my set attributes so you can name each of them. And I'm going to make it the small one. And I'm going to name the signal name and the index. So the first signal in, I'm going to go ahead and create constants for the other two. So the first signal is dynamic pressure voltage. Then the second second signal is don't forget to connect in between them. So index 1, and that's static pressure voltage. Then the third one is your dynamic pressure mean, voltage mean, and then the third one is the fourth one is standard deviation instead of mean. Then the fifth one then your fifth one, so that's 1, 2, 3, 4, 5. You follow it. Dynamic pressure. So this one dynamic pressure in pascals. Then your sixth one is velocity. And then your seventh one Yep, this one's supposed to be 5. This one's supposed to be 6. Then your seventh one is static pressure, voltage mean. Your eighth one is static pressure, voltage, standard deviation. Then your ninth signal is your relative static pressure. In pascals. And again, don't forget to connect the ins and outs. And then your 10th is your ambient pressure. Then your 11th is your absolute static pressure. Then your 12th is your density. So this is density, and that's in kilograms per meter cubed. Then your 13th is your height. So don't forget to change that height location for every location you're at in meters. Then your 14th signal is your first Bernoulli's constant. And the units for that is pressure. So Bernoulli constant equation 1617, and pascals is the units. And the 15th one is the second Bernoulli's constant. And I'm going to just copy the previous one so I don't have to type it. And this one is equation 18. And then finally, we're going to connect all of this to a write to measurements file. Under output, write to measurements file. And I'm going to use one header per segment, one time column only in tabular, and then use next available file name. Click OK. I'm going to shrink it to as small as it will go. And then I'm going to take my output from all the naming, create a control for enable, and create a control for the file name, and then create an indicator for saving data and an indicator for where the path is going out. And that's the VI that you create for this lab. So keep in mind that it looks a little confusing here, but you can always follow the wire on where it's going. So you can highlight it and see where it's going. Like this one right here goes to row infinity. And then you have absolute pressure. You can find out where that one goes. And you can move them over a little bit, even though they cross over each other. Where there's a dot, it means it's connecting, and when there's no dot, it means it's not connecting. And that's pretty much it for this tutorial. Now I'm going to go to my front panel and organize it some more. And what I'll do is I'm going to move up the DAC controls, move up the controls for the height, the ambient pressure, and that. And then I'm going to move the controls for saving down here. And I'll move the saving data one right next to the enable. Shift this down a little bit so I can read it better. Shift right over a little bit. And then file name out, I'll shift down here. And then extend this so I can read where it's going. And this is the setup for the VI. This is how you do the VI for Bernoulli's lab.